Well, hello standard geometry students and welcome to online geometry again. We're going to get started into chapter 12 where we're going to be going round and round because chapter 12 is a whole chapter on circles. It's my favorite chapter. So let's go ahead and get started. First of all, a few announcements. There will be a quiz this week, so make sure that you take your quiz over chapter 11. So look at your assignments and make sure you've got that. Make sure that you contact your teacher if you're having any issues. We want this to be as easy for you as we possibly can. So reach out, call your teacher, email your teacher. We're happy to help you. Let's go ahead and get started then in chapter 12. In chapter 12, we're going to be looking at 12.1 and 12.2 this week. So 12.1 is lines that intersect circles. So the first question I asked is, where could the line be? And how many points of intersection then is the second question. So let's take a look at that. Could my line, let's take a look at a different color. Could my line be on the outside like this? Well, that is not going to intersect the circle, is it? So we're not going to be able to have it on the outside like that. So let's use a different color because we said we're looking at lines that intersect. What would happen if I made a line like this? Would that line intersect the circle? Obviously, yes. But now the question is, how many points of intersection would there be? Now, some of you may think that it's just this one point, and we'll call that point A. But remember from quarter one that a line that has those arrows goes on and on and on forever. So we actually have 2 points of intersection. Those 2 points of intersection are called a secant. So a secant is a line with 2 points of intersection. And that could be a secant, could end up being any line. It contains a lot of different points. I could make a secant here, I could make a secant here, I could have an infinite number of secants. So let's go back to that first question. Could I have a line that just touches at 1 point? We know no points, that didn't work. 2 points, that works, and there's a whole bunch of them. But what about just 1 point? Well, I could if it just brushes right next to the circle. So I could end up with a line like that. That is called a tangent line, or we just call it tangent for short. So my tangent line is a line that intersects a circle at 1 point. My secant is a line that intersects the circle at 2 points. And remember, we already had a lot of vocab about circles. So reminder, your center of the circle is not part of the circle. So if I want to look at this as circle O, I can certainly name it circle O. And that would be my symbol for circle O, is just a circle with a dot in it, and then followed by the capital letter. Remember that a diameter goes through the center of that circle and connects 2 points on the circle. So that would be a diameter. Remember, a radius comes from that center O and comes out. So we still have all those things that we've had before. Okay? The radius is actually a special segment because it goes right through the center of the circle. But we also have that as a chord, C-H-O-R-D, chord. Now a chord is a segment, like a radius is a segment, like a diameter is a segment, a chord is a segment. But a radius is not a chord because it doesn't touch 2 points on the circle. Our diameter would be a chord because it touches the endpoints on the circle. But that's the longest chord. I could have a chord here. As long as it starts and stops on the circle, it's a chord. And I also could say that segment AB is a chord because that's a segment that starts and stops on the circle. So you could say then that a secant is a line that contains a chord. Now I know that that's a lot, and we're going to go over that here in a little bit, so don't get frustrated. It's just an introduction to all these words. Let's take a look at a couple of facts that happen. Okay, and I'll slow down and make sure that you have it all in your notes here. Okay, so when we look at a radius and a tangent line, then we know that that radius and that tangent line have to be perpendicular. That tangent line, remember, is the line that intersects the circle at just one point. That was called the point, and that's called a point of tangency. Now again, don't worry about writing that right now. I'll get that to you in a little bit. So my point of tangency is just that one point where the tangent line intersects. And remember, it has to be a line, so it goes on and on and on forever. So these would be tangent circles. This line would be a tangent line. And now what we're saying is if you put in the radius, so let's go ahead and put that in a darker color. If you put in the radius, which obviously is from a point on the circle to my center, then that has to be perpendicular to my tangent line. So if my line was horizontal and I put in my two tangent lines, that equation, or those two radii, that equation of that line, remember, would have to be a vertical line. And remember that you had that before also. If it's a vertical line, then it's going to be an x equals equation. So it kind of depends on where this radius is. If my radius went through 0, that would be the line x equals 0. Okay? But remember, if I had perpendicular to the tangent, so just draw in my perpendicular to the tangent, and now I have a horizontal line. I wanted to remind you that a horizontal line is a y equals equation. Again, we had that from before. So I have x equals equations for vertical lines, so remember that as we get into some examples, and y equals equations for my horizontal line. And we're looking at the radius, the line that the radius connects to, not the tangent line. The tangent line would be an x equals equation. The tangent line here would be a y equals equation. So if I look at the tangent line, you have to look at, is the tangent line, so that would be this line, horizontal or vertical. So if that's horizontal, that would be a y equals. Okay, so you have to be careful. If they ask for the tangent line here, the tangent line would be vertical, and so that would be an x equals. So it depends whether they're asking for the tangent line or the radius, okay, as to whether it's an x equals or a y equals. So be careful on that, and we'll get to some examples on that in a little bit. Okay, then we have a fact, and this is kind of the most important here in 12.1, and we'll pretty much be done with 12.1. I told you it's just really a lot of vocab this week. Okay, but we have two tangent segments. So the tangent segments are just part of a tangent line. So recognize if I continued on, they would only touch at that one point. They would only touch at that one point. And it says two tangent line or segments from the one exterior point must be what? Well, if we think back to what we just said, every time I put in a radius, it has to be perpendicular to the tangent. So if I put in the radius from A, circle A, it's perpendicular to the tangent. Well, look at this. If I just draw from A to X, what do I now have? Well, AX is congruent to AX by what? You remember the reflexive property. And then my radii in one circle are also going to be congruent. So what's going to happen to these two triangles? You guessed it. We really are never getting past that, are we? The triangles are going to be congruent. Okay? So if I have two congruent triangles, we can now answer the question, two tangent segments, so in this case it'd be this segment and this segment, if they come from one exterior point, are always going to be congruent. So those are the two big facts that we're trying to get across here in 12.1. If I have a radius, it's always perpendicular to the tangent line at the point of tangency. Okay, so be careful as to whether the tangent line is going horizontal or the radius is going horizontal, okay, and which one they're asking for. And then two tangent segments from one exterior point are always the same. So what that's saying is if this is 10, then this side, we'll call it x, x would have to equal what? Of course, 10. Okay, let's go on to 12.2 so we don't get too far. Oh, we have a new little guy here today. You know why I had to make a new little guy? Because, you know, it's my birthday coming up here not very long. It's just another week away. And every year on my birthday, I got baby chicks. So I thought we could have little baby chicks. And he's trying to remind me again, like the rabbit used to, is we haven't answered the question from last week. So the question from last week, here you remember it. Why didn't the math student share her answer? Why didn't the math student share her answer? She was too squared. She was too squared. Okay, this week our question is, what do you call when you take a balloon, blow it up, and you push on it? So what's that force when you're pushing on a balloon called? Okay, so think about that. What is the force when you're pushing on the surface of the balloon called? And let's go ahead and take a few notes from 12.2, and then we'll put all that vocab together. 12.2 is looking at arcs and chords. So arcs and chords are going to be really, really easy for us because remember we talked about chords before. They're just from one point on the circle to another point on the circle. So BD is a chord. So all we need to look at is the new notation for arcs. Arcs are simply part of the circle. So I have a lot of different arcs here. So I said the measure of arc DC, and that's how you would write when I look for the measure of arc DC. DC would come from D to C. Well, remember the diameter makes 180 degrees, so that would just be 100 degrees. That makes sense? 80 here, 100 here. Now, look at how you're going to name it if it's arc DEB. So if it starts at D and goes all the way over, so it has to start and stop at those endpoints. So you're looking at D to B. Well, that makes a semicircle. How many degrees are in a semicircle? Perfect, 180 degrees. How about the measure of arc DBC? So I go DBC. Now I got to be careful because I've got to stay as an arc, so I have to stay on the circle. D all the way on the circle through that to C. So I'm really taking 180 plus the 80, so I'm going to end up with 260 degrees. Okay, and then we look at our angles. These are called central angles. And again, we'll look at that as a vocab word in just a minute. But a central angle is really quite easy because guess where its vertex is? The center of the circle. So I'd have central angle, angle CAD would be a central angle, and angle CAB would be a central angle. And it's very, very easy because the central angle is exactly the same as its arc. So this angle is 80 degrees. This angle is 100 degrees. So the measure of angle BAC is just 80 degrees, and DAC is just 100 degrees. So our fact from this is a central angle, and I do want you to write that in your notes. A central angle is always equal to its minor arc. So whatever the angle equals, then the arc is equal to that. Okay, and then we start looking at what happens with the chords. Well, this is a very important fact. All radii of one circle are congruent, so just look for congruent triangles, and you'll be able to see things like what happens when I have congruent central angles. Well, if I have congruent central angles and my radii are all congruent, so let's go ahead and label our radii, that would mean then if the central angle is congruent to this central angle, that the triangles are congruent. So again, I just look for congruent triangles. Well, if that triangle is congruent, then my chords are going to be congruent because I'd have this triangle congruent to this triangle, so therefore BC is congruent to DE. Now I know that sounds like a lot, so stick with me. It's really just about vocab this week. So the big things there, two facts that I want to make sure you've got from 12.2. A central angle is equal to its minor arc. A central angle is equal to its minor arc. Make sure you put that in your notes. And all radii of one circle are congruent. In order to have congruent circles, you'd have to have the same size radii. Okay? So if I have congruent circles, then they would end up having the same radii. And then look for those congruent triangles to answer some of those questions today. Now, let's make sure you've got the vocab down. So this is the part where if you need to, you can just stop the video and make sure that you have all the vocab down. So let's make sure we've got the vocab. So we're looking at a lot of vocab in 12.1 and 12.2 that we're going to be using for the rest of chapter 12. Okay, so let's see if I can make the vocab come in here and still see it all. Okay, so vocabulary. So we're looking at a secant, which would be the line containing the chord, and then the chord, any line that or segment, excuse me, not a line, a segment that stops and starts on the circle. The circle is named by its center, so that one would be circle A. The tangent lines would be the ones that touch in one point. So line HB would be the tangent line, and point B would be the point of tangency. Okay, so it's not so bad. It's just a lot of new information, a new vocabulary. Congruent circles have to have the congruent radii. So if I make this a congruent circle, it would have to look exactly the same size. That's kind of easy. Concentric circles. Now we haven't had that yet, but you see that all the time. Target. You go to Target, concentric circles. So they have the same center, but they don't have the same radii. So if I made a small circle inside here, kind of looks like a bullseye or maybe another one, you see how it would look like a Target ad? And that would be concentric circles. And then remember our central angle, pull that up a bit, a central angle, the vertex is on the center of the circle and it contains two radii. So it could be, that's a chord and that's a chord, okay? So it contains my central angle, that would not be a central angle. My central angle would have to be, let's go ahead and look at making one here. So if I connect A to D, D, A, B would be my central angle, because it has its vertex at the center and then it has two radii. So that would be my central angle. Okay, our last of our vocabulary we have talked about before briefly, so I want to make sure you've got that in your notes. That was the ones I was just giving you examples of: minor arcs, major arcs, and semicircles. Without the M's, it doesn't mean measure, it just means the set of points. So here we're looking at saying if I had a minor arc, EB. So if it just has two letters, you have to go the shortest way. So that would just be this part of the circle, starting at E and ending at B. That's the minor arc. The major arc is greater than 180 degrees. So notice I had to say three letters, C, B, E. That means I start at C. I don't go across. I have to stay on the circle. I have to go through B, and I have to end at E. So I can't go this way because that would be at E first. So you have to go in order. C to B to E would start here and go all the way here. So a major arc, bigger than 180 degrees. That makes sense? Okay, and then my semicircle, that's the easy one. It's just going to be equal to 180 degrees. So the arc, again, don't name the diameter. The arc would be named with three letters. C, D, B, starts at C, goes through D, and ends at B. Okay, and remember you can stop and take a picture of that and make sure that those go into your notes. Okay, and then we're going to be looking at, I need to raise it up just a little bit. Okay, we're going to be looking at guided practice problems next. So make sure that you look at your reteach, get those printed out, and have a great week learning geometry. Bye.